Assalamualaikum and good morning, everyone. So today we are going to learn on chapter 6, PID controllers, and this will be our last chapter for AC. Okay. So in this topic, basically PID controllers is there are many controllers exist for controlling a system, but in this subject we are going to learn on one of the controllers, which is PID controller. So let's look at what is PID controller is about. Okay, so let's say suppose that you have a system that needs to be controlled. So your software gives command to the system and the system will respond to your command. For example, you ask maybe an antenna to turn a certain degree, and then maybe for example you ask your car wheels to rotate for a certain number of rotation. But is the system will the system follow exactly what you want? For example, will the wheels rotate 15 times, or maybe it will rotate maybe 16 or 14 or maybe 15.5, for example. How accurate is the system will respond to the command that you give. So the inaccuracy made by the system is what we have learned so far, the stability. So we want to make sure that the system follow accurately what you said. With maybe a slight error, okay, not not a large error, but maybe a very small error. So we have learned so far about open loop control system. So for an open loop control system, let's say temperature measurement. So when you give a temperature to, okay, sorry, for example, aircon, okay. For example, you ask the aircon to cool the room for maybe 24 degrees Celsius, and then the system will produce cooling so as to make sure the room is at 24 degrees Celsius. But if the system has no sensor that can measure the room temperature, then the cooling will keep going, okay? No matter how much you set, for example, 24, even though the room has already reached 24 degrees Celsius, but the system will keep cooling the room because it has no sensor that can measure the room temperature and then measure the error difference between the desired the input temperature and the actual temperature. So open loop system basically has no sensor that can measure the error difference between what you set and what the actual output. But for a closed loop system, the same thing, the same example, let's say an air conditioner. So if you have an air conditioner that has sensor that can measure the room temperature, then it will tell the system that the room has already cooled less than 24 degrees Celsius, maybe 23. So please stop cooling the room. So the aircon will stop produce more cooling to allow the temperature in the room to increase back to 24 degrees Celsius. And if the room temperature increase more than 24 degrees Celsius, then the sensor will detect the increment and will tell the air conditioner to start cooling so as to reduce the temperature back to 24 degrees Celsius. So here we have a sensor and also a controller that can measure the error difference. So the most simplest controller in a system is on and off control. For example, like your switch in a room. For example, let's say you want to brighten your room, so you open the switch to allow the lamp to turn on, and when you want to uh, turn off the light, then you just switch off the switch. Okay, so this controller requires your action. Okay, meaning that not really at automatic, and sometimes it can cause overshoot or undershoot. So how this cause overshoot and undershoot is from this example here. So let's say a system that has a signal that is oscillating, for example. So the blue one here is the state when you turn off and turn on the switch. So when you turn on the switch, then the signal will increasing. And then when you turn off, then the signal will start decreasing. So what happened here is that when you turn off the switch, then the signal will take some time to reach uh, a zero state. Okay, so I said this, the bottom state here as a turn off state and the top here as a turn on state. So when you turn on, then it will take some time to reach maximum. When you turn off, then it will take some time to reach minimum. So the time taken here is something that we don't want it to be too long. We want it to be as fast as possible. For example, if we turn on, then it will reach maximum as fast as possible. We turn off, then it will reach minimum as fast as possible. So because of some issue or stability problem in the controller, then it will take some time to reach minimum or maximum. So in PID controller, so this slide introduces PID controller first before the actual problem about the stability, but later I will explain more about the stability. Okay. So for PID controller, PID means proportional, integral, and derivative controller. So far we have learned about transfer function. So the transfer function has the symbol S here. So the S here represent the frequency response, okay? Frequency of the transfer function. So for proportional controller, the equation will be you just have a gain Kp here. We call it proportional gain. For integral controller, we have an integral gain Ki, but the equation will be Ki over S. For derivative controller, we have a derivative gain Kd, but in the transfer function of the controller, the equation will be Kd times S. So the controller has its own transfer function also. So your system, GS, has its own transfer function. So the GS comes from maybe like for example your project comes from gears, mechanical system, plot diagram, and so on. And controller, the PID controller, the transfer function is always like this: Kp plus Ki over S plus Kd times S. And then you can simplify this, becomes Kds squared plus Kps plus Ki divided by S. Okay, so Kd is the derivative gain, Kp is the proportional gain, and Ki is the integral gain. Okay, so the PID controller, usually we symbolize controller as a single subsystem, but in reality, the PID controller has three components: P, I, and D, and then it is arranged in parallel, and you will sum it together and becomes one controller. Okay, so this is the PID controller that I just explained. So we have a controller here, and in the controller we can put PID controller. So this is the transfer function for PID controller. And this is the PID controller in frequency domain or S domain. And if you want to convert into time domain, then it becomes KPE plus KI integral of E plus KD derivative of E. Okay, so that's why it's called KP as proportional, KI as integral, and KD as the derivative. Okay, so back to the stability problem in control system. So usually if you have a time response for the output, when you plot the time response, then you will get the time response as shown here. So what you desire is that you want it to reach this target value here as fast as possible without any ripple or any oscillation and no overshoot. But it is almost impossible to get that kind of time response. Usually your time response will have an overshoot, some undershoot, and then oscillation. After it oscillate, then it will reach a value that is not exactly the same as the target value. So here, the value reached by the time response has what we call steady state error. So error is about, in here, the error is about 10%. And also we have a rise time here. So the signal will take some time to reach the target value. So the time taken to reach the target value here is called rise time. And then settling time is when the signal or the time response, the oscillation has become less and less. Okay, so here we call it settling time. So in a control system, we desire a time response that has no overshoot, rise time as fast as possible, possibly zero rise time, and zero steady state error. So if you, for example, if you do FYP related to control system, maybe later or now, then maybe if your supervisor asks you to tune PID controller, then you will tune your PID controller so as that the time response will have no overshoot, zero rise time, and also zero steady state error. So you need to keep tuning until you get the time response that you desire. So you need to control for better performance. So you use PID and choose whatever response that you want, whatever target that you want. Okay. So the required is this black line here. So you want the system to have this black line. But in real life, it is very impossible to get this black line. Okay, impossible because maybe in theory related to control system and signal and system, there is a phenomenon we call Gibbs phenomena. So Gibbs phenomena ni, it says that the signal will have certain overshoot and oscillation before reaching steady state value. So here, if you use PID controller, so you will get probably this red line here. This is the best uh, PID controller performance based on your PID controller. Okay. or possibly a bit higher. Okay, so if you tune PID controller later, then the best graph is the red line here. Okay, so we don't want the system to have this dotted line here, has too much overshoot or undershoot, and stable, but it will take some time to reach a steady state. And you also don't want this dotted line on the bottom here, because the response is too slow, meaning that it takes so long time to reach the target value. Okay, so we don't want this both. So the red line here is what we call sufficient. Okay, just enough, cukup je. Okay, so proportional controller first. Okay, so a proportional controller attempts to perform better than an on-off type controller. So as the gain increase, the system responds faster to the changes in set point, but becomes progressively underdamped and eventually unstable. So for proportional controller, if you increase the gain, then the rise time will be faster, but the system will become underdamped or will produce more overshoot and more oscillation. So if you increase more gain, proportional gain, then the system will be more unstable, but the rise time will be faster. And the final temperature lies below the set point for the system because some difference is required to keep the heater supplying power. So another setback of proportional controller is that it will produce a certain amount of steady state error. Okay, it will not reach the target value exactly, but it will produce some steady state error. So if you use a combination of proportional and derivative controller, then the stability and overshoot problem that arise when a proportional controller is used at a very high gain can be mitigated by adding a term to the time derivative. So if you add derivative controller, then derivative controller will encounter the setback by proportional controller, which is the stability and overshoot problem, meaning that derivative controller will reduce the overshoot of the system. So the value of damping can be adjusted to achieve a critical damp response. Okay, so if you add time derivative and increase the time derivative, the derivative controller gain, then the overshoot will reduce and the system will become more stable, but it doesn't reduce the steady state error. Okay, and then you can also combine proportional, derivative, and also integral controller in a single controller. So although PD control deals neatly with the overshoot and bringing problems associated with proportional control, however, it does not cure the problem with steady state error. Fortunately, it is possible to eliminate this while using relatively low gain by adding integral term. So if you add integral term, then the integral controller will reduce the steady state error. So if you look at this graph here, the green one, then the effect of derivative will reduce the overshoot and will reduce the damping. The effect of integral controller is it reduces the steady state error, and the effect of proportional controller is it reduces the rise time. Okay, but you need to adjust the gain for each of the controllers. Okay, so the basic characteristic of PID. So a proportional controller will have the effect of reducing the rise time and will reduce but never eliminate the steady state error. An integral controller, however, will have the effect of eliminating the steady state error, but it will make the system transient worse, meaning that if you use only integral controller without KP and KD, then it reduces the steady state error, but it will produce more damping and more oscillation. Okay. And lastly, if you use derivative controller, then it will have the effect of increasing the stability, reduce the overshoot, and improve the transient response. But derivative controller will not eliminate the steady state error, same as proportional controller. Okay, so this table summarizes the effect of PID if you use them individually. Okay, so KP will reduce rise time, but will increase overshoot and also decrease slightly the steady state error. For KI, you you will get a decreased rise time, but increase overshoot and settling time, but eliminate the steady state error. And lastly, for derivative controller KD, it will reduce the overshoot and also decrease the settling time, but has a small effect on steady state error and rise time. Okay, so the rest of slide 6A is about PID controller example. What happens if you use P, PI, PD, and PID? Okay, so I skip on this because tak keluar final on the theoretical part. Okay, so we go straight to tuning the PID controller. Okay, so PID controller, as I explained just now, has three components or three types of gain. You have proportional gain, integral gain, and also derivative gain. So we have to tune this gain individually using programming software, for example, MATLAB, to get the time response as what we desire. Okay, so more than half of the industrial controllers today utilize PID or modified PID control schemes. So many different types of tuning rules, okay, that have been proposed. For example, like manual tuning, online automatic tuning, gain scheduling. So when the mathematical model of the plant is not known, and therefore analytical design methods cannot be used, PID controls prove to be most useful. So plant is your GS just now. So sometimes we don't know about the plant, what is the transfer function. So luckily in your project, you know the plant already because you derive the transfer function. But sometimes the transfer function can be derived. Maybe the system is too difficult to derive. So you can use PID controller without deriving the plant transfer function. So to tune the PID controller, so we put PID controller in front of plant. So the PID has the component KP times 1 plus 1 over TIS plus TDS. Okay, so this is you factorize KP, okay? So that's why you get TI and TD. So you can design PID controller if the plant is complicated and you cannot obtain the mathematical model. So the tuning method that we will teach to you in this subject is what we call Ziegler-Nichols rules. So Ziegler and Nichols proposed rules for determining values of the proportional gain Kp, integral time Ti, and derivative time Td based on the transient response characteristics of a given plant. So the rules here is that you need to know the transient response of the plant. Okay, only that. You don't need to know the transfer function of the given plant. So such determination of the parameters of PID controllers or tuning of PID controllers can be made by engineers on site by experiments on the plant. So basically you need to do the experiment on the plant, get the transient response, and then from the transient response, you will do something to tune the value of gains based on Ziegler-Nichols. So such rules suggest a set of values of Kp, Ti, and Td that will give a stable operation of the system. However, the resulting system may exhibit a large maximum overshoot in the step response, which is unacceptable. So we need a series of fine-tunings until acceptable result is obtained. So there are two methods. So the first method is the first method of tuning rule, Ziegler-Nichols first method of tuning rules. So firstly, we do experiment to obtain the response of plant to a unit step input, okay? So when you apply a unit step input to the plant, your GS, and then you will get the time response CT. So the plant involves neither integrator nor domain complex conjugate poles. Okay, ni some theory, okay? This method applies if the response, the time response, CT here, to a unit step input, UT, exhibit an S-shaped curve. So if you get CT S-shaped curve, then you can use the first method of tuning rule. So such step response curves may be generated experimentally or from dynamic simulation. Okay, so you can use experiment or you can use some simulations, okay, to get the S-shaped curve. So from the S-shaped curve, you need to determine two things, okay? So the first thing you need to determine is the delay time. So the delay time is the time taken for the CT to start increasing, okay? So it's approximately from here until maybe here, okay? Masa dia nak naik tu, itu time dia. And the time constant, what you need to do to get time constant is you need to draw a tangent line on the S curve, and then the intersection between the line and the steady state value, and 0 here is the time constant, okay? So from the value L and T, so you can determine the transfer function. So this transfer function is from the graph, okay? Kita tak guna yang ni. This is the plant transfer function. So to obtain the value of gains, the Kp, Ti, and Td, so you need to use this table. Okay, kalau keluar final soalan PID, buka je nota, okay? Dalam nota carilah table ni. So usually in exam or in final exam, we use PID controller. So for PID controller, Kp equals 1.2 times T over L, Ti is 2 times L, and Td equals 0.5 times L, okay? And then from there, from the value of Kp, Ti, and Td, you just substitute into the transfer function of the controller. Okay, so this transfer function is given already ni kat sini, okay? Sama je transfer function dia, tak berubah pun. Okay, so you just substitute the value of Kp, Ti, and Td, and in the end you will get 0.60 times S plus 1 over L squared over S. So thus the PID controller has a pole at the origin and double zeros at S equals 1 minus 1 over L. Okay. Okay, so quiz 12A, tiba-tiba je. Okay, so design a PID controller using Ziegler-Nichols method. Step response of the system is given by the curve. So the curve here is S-shaped. So from the curve, estimate secara roughly lah, okay, the value of L and also the value of T. Okay, kalau dalam exam nanti diberi curve macam ni, try to nak kata print pelik juga kan, maybe secara kasar ukur pakai pembaris ke yang value of T tu. Okay, so in this quiz you need to obtain the value of L and the value of t. After you obtain value of L and T, you need to calculate the transfer function for the controller, the GC here. Okay, before that, you need to determine Kp, Ti, and Td first. Okay. Kp, Ti, and Td. After you determine Kp, Ti, and Td, you calculate the transfer function for the controller. After you calculate the transfer function of the controller, you get GC here. And then after you get GC, you simplify the transfer function, simplify the block diagram to obtain the final transfer function of the system. Okay, so that's basically the steps for this kind of question. Okay. Okay, so example tak banyak untuk PID. So example dia memang ni je lah. Okay. So maafkan saya kalau tak banyak example. Okay, so just now is the first method, the Ziegler-Nichols first method. Now we look at the Ziegler-Nichols second method. So for second method, we first set Ti equals infinity and Td equals 0. So basically we use only the proportional gain. Okay. So we do the same thing. We use only the gain, and then we do experiment on this system to get the time response. So we increase Kp from 0 to a certain value. We call it the critical value, KCR. So this value of KCR will cause the CT, the time response, to exhibit sustained oscillation. Or what we have learned so far, sustained oscillation is for a system is when the system is marginally stable. So marginally stable meaning that the value of K when the system or the root locus crosses the JW axis crossing. Okay. So for marginally stable system, the time response will oscillate, but the oscillation is constant. Okay, meaning that the period of the oscillation is constant. So the period of oscillation, PCR here, is the period for sustained oscillation. Okay. So you increase Kp until KCR, at which the time response oscillate sustainably, okay, or has marginally stable system. Okay, so Ziegler-Nichols suggests that we set the value of the parameters Kp, Ti, and Td according to the formula shown in the table. Okay, so for the second method, the table is different from the first method. Okay, so you obtain your KCR and also determine the PCR. Okay, after you determine KCR and PCR, you calculate Kp equals 0.6 KCR, Ti equals 0.5 times PCR, and Td equals 0.125 times PCR. So you get the gains for PID. Okay, so this is the same equation for transfer function of PID. So you just substitute Kp, Ti, and Td with the value from the table, and you simplify. Okay, thus the PID controller has a pole at the origin and double zeros at S equals -4 over PCR. Okay, yang ni boleh baca sendiri. Okay, let's look at an example of PID, Ziegler-Nichols second method, tuning rules. Okay. So consider the control system shown in figure 10.6, in which a PID controller is used to control the system. The PID controller has the transfer function given here. Blah, 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 blah. Let us apply Ziegler-Nichols tuning rule to obtain Kp, Ti, and Td. Then obtain a unit step response of the curve. Ini selalu soalan tak tanyalah nak 25% overshoot semua. Soalan dia selalunya so cari KP, TI and TD je. Okay, selalunya soalan Hakim beritahu using second method ke ataupun first method. Okay. Okay, but in this example, it uses the second method. Okay, so the first thing you need to do for the second method is you need to assume that the PID controller has only KP. Okay. Meaning that TI equals infinity, TD equals 0. So tinggal KP je. So from there, you simplify the block diagram. So you simplify the block diagram here with GC equals KP. So you get KP divided by S times S plus 1 times S plus 5 plus KP. So the value of KP that makes the system marginally stable or sustained oscillation can be obtained using Routh-Hurwitz criteria. Okay, kena guna Routh-Hurwitz table. So we use the denominator. So we take the denominator, kembangkan S cube plus 6S square plus 5S plus KP equals 0. And then arrange in Routh table. So start from S3 and then S2. Susun alternatingly 1, 6, 5 and KP. And then determine S1 and determine S0. So examining the coefficient of the first column, we find that sustained oscillation occur if Kp equals 30. Okay, so you use the same method to determine the value of Kp when marginally stable. So Kp equals 30. So we take S1 here and assume equals 0. So you get Kp equals 30. Thus, the critical gain KCR. So KCR dia adalah 30. So KCR just now is the value of Kp when the oscillation is sustained or marginally stable. So with the gain Kp set equal to KCR, the characteristic equation becomes S cubed plus 6S squared plus 5S plus 30 equals 0. And then to find the frequency of the sustained oscillation, we substitute S equals J omega into the characteristic equation as follows. Okay, so we use this value here. Substitute J omega, from which we find the frequency of the sustained oscillation to be omega squared equals 5. Okay, or omega equals square root 5. Hence, the period of sustained oscillation is PCR equals, so the formula is 2 pi over omega. So omega is square root 5. So you get PCR equals 2.8099. So you use the value PCR here and value KCR that we obtained just now into the table. Okay, so you use KCR and PCR, substitute in the table, so you get KP, TI, and TD. Okay, so in this example, the value of KP equals 18, TI is 1.405, TD is 0.35124. So we take this value, substitute into the transfer function of the controller, simplifykan. Okay, gantikan dalam PID controller tadi, and then try to simplify the block diagram to get the final transfer function C over R. Okay. Okay, this is how if you want to use MATLAB. Okay, so for quiz 12B, question of quiz 12B, So a closed loop control system shown in figure 1 is used to stabilize a plant with transfer function GS. So a proportional gain K is used to change the system output CS from unstable to marginally stable at critical gain KCR. If the transfer function of GS is given as this, find value of K equals KCR for marginally stable system. So meaning that you need to simplify first the block diagram, use Hurwitz criteria, and find KCR. And then lastly, design a PID controller for the system using Ziegler-Nichols tuning rule. So here we have KCR, so you know that this is second method. Okay, derive the final transformation of PID controller. Okay, so you use the Ziegler-Nichols method, second method. You get KCR, you determine the PCR, first determine the frequency and then determine the period of the sustained oscillation. Use value of KCR and PCR into the Ziegler-Nichols second method table. You get Kp, Ti, and Td. And then from the value Kp, Ti, and Td, you substitute into the transfer function of the PID controller, this one, and then obtain the final transfer function of PID controller. Okay, macam simple tapi try dulu. Okay, itu je untuk hari ni. So sebelum kita tamatkan kuliah, so I want to discuss about your final exam. So final exam bila entah saya tak tahu. So final exam you will have 20%, okay, for final. So 20% final exam and you have 4 questions. Okay, so final exam ni walaupun dia 20% sama macam midterm, tapi dia punya soalan still 4, okay, dan still 3 jam. Okay, nanti janganlah post dekat UMP troll ke. Soalan 2% je tapi sampai 4, nak 3 jam. Ingat kita ni tak ada, okay, saya berhenti merepek. Okay, so 4 soalan 3 jam. Okay, so soalan pertama, so topik dia will be gearing and also so gearing ni determine transfer function. And then ni soalan A. Soalan B dia pula, from the transfer function you give input, so determine the output using partial fraction, okay. Okay, so benda ni kita dah belajar masa awal-awal dulu macam mana nak determine the partial using partial fraction, okay. So ni basically before midterm punya, okay. See, so question number 2 will be about root locus. So root locus, study lah semua benda yang berkaitan root locus, but also study determine whether a point is on root locus. Okay, determine macam mana nak determine whether a point given is on a root locus. Okay, question 3. Question 3 will be about A will be about reducing block diagram. And question B will be about dot plot. Okay. And lastly, question 4 will be about Hurwitz criteria and also PID. Okay, PID second method. Okay, dah bagi tahu banyak dah. Okay, so study. Apa-apa tak faham boleh tanya, okay. And then okay, so that's all for our class. Okay, so your project already have part 1, 2, 3, part A, B, kan? So if you think this is enough, okay lah. Okay, saya tak nak tambah dah. Kalau rasa macam sir nak lagi part C ke, part 4 ke, beritahu saya. Okay, saya tak rasa ada yang nak. Okay. So reminder again. So your carry mark is 60%. So quiz kita ada 12. So sama macam last sem, quiz 25%. Okay. So project part 1, 2, 3, maybe part 1 and 2, 15%. So part 3A and B is another 20%. Okay. So siapa yang kalau quiz hantar lewat, saya dah kata tolak markah. Kalau projek ni maybe saya consider lah kot. Okay. Okay, so tu je. Okay, so apa nak cakap? Kelas hari Rabu saya tak nak buat kelas, okay? Tapi korang ada quiz yang tak dibincangkan. So plan asal tak nak buat sebab ada kerja lain. Tapi if you want a class, let me know in WhatsApp group, okay? Kalau tak ada respon, tak nak kelas lah maksudnya. Okay? And so today's class will be the last one if you don't want class on Wednesday. And also if apa nak cakap? Ni last, kalau last class meaning that this is our last meeting, okay? And kalau jumpa saya nanti kat UMP next sem, tegur lah sebab saya pun tak kenal maybe half of you saya kenal from previous class, okay, macam CP for example. And jangan takut nak tegur saya sebab saya tak kenal awak kena tegur saya dulu sebab saya tak tahu awak siapa, okay. And also maybe related to FYP. So siapa yang berminat untuk buat FYP SEM 1 2021 2022, jangan segan-segan tanya saya, contact saya, okay. Sebab saya akan offer tajuk pada SEM 1 tahun depan, okay. Okay, so that's it for our class for today. If you have any question related to AC or anything else, any matters, you can contact me through WhatsApp, okay. So thank you very much for your cooperation as throughout this semester, and see you again inshallah next time. Assalamualaikum and goodbye.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.